In this video, we're going to expand upon the concept of chemical reactivity that was introduced in the previous video. Summarizing what chemical reactivity is, it is simply a measurement of how elements are able to gain or lose electrons in order to form the compounds that they do when they react together. Even with covalent compounds, because of an electronegativity difference, all elements can either be looked at as gaining or losing electrons from one another. And if these elements are grouped together in terms of their reactivity, with the most reactive being placed at one end of the group and the least reactive at the other end, for nonmetals and metals, we can see these two tables, which are what we call activity series, can be written. And our job in this video is to understand the rationale behind how these reactivity series are actually constructed. And we're going to start with the nonmetals firstly because it's shorter, and secondly because the justification behind all of the elements positioned is actually relatively self-explanatory. All of the placement of elements in terms of how reactive they are can all be justified using atomic radius, ionization energy, electronegativity, and the number of valence electrons that each nonmetal possesses, which are basically the subject of the previous unit. For example, if we compare fluorine and chlorine are both halogens, which means we can't look at the number of valence electrons directly because all of them are, or both of them rather, are halogens, and therefore each of them has 7 valence electrons. However, because fluorine is one level on the periodic table up from chlorine, that means that fluorine has a smaller atomic radius, meaning that its valence electrons are closer to its nucleus than chlorine, and therefore they would have a higher ionization energy, meaning that it takes more energy to remove an electron from fluorine than it does from chlorine, giving fluorine the highest electronegativity on the periodic table. Simply put, because of fluorine's small atomic radius and very, very tight hold over its valence electrons, fluorine is even better at gaining one valence electron than chlorine is, even though chlorine has more protons in it, because its atomic radius is larger, making its valence electrons farther from the nucleus, and therefore the attraction between the valence electrons and the nucleus is weaker in chlorine. If we compare fluorine to the third element in the nonmetal activity series, oxygen, the comparison is even more obvious, because oxygen, unlike the halogens, only has 6 valence electrons, which means that it needs to gain 2 electrons rather than just 1, meaning that fluorine is even better at gaining electrons than oxygen because it only needs to gain 1. If we look further, fluorine also has more protons than oxygen. Fluorine is atomic number 9, whereas oxygen is atomic number 8. And therefore, because fluorine has more protons, its nuclear charge, and therefore its attraction to its valence electrons, is even stronger than oxygen, pulling them closer to the nucleus and making them even harder to remove than oxygens as well. So it's no surprise that fluorine occupies the very top of the nonmetal activity series. And when we talk about nonmetals, when we say most reactive, we can simplify this by saying that the higher an element is on this activity series, the easier they are at gaining electrons, meaning that fluorine is the easiest element for it to gain an electron, whereas all the way down, even below phosphorus, would be an element like carbon that basically neither loses nor gains electrons at all. Now, all of this still applies to the metal activity series as well, and we see some very obvious comparisons. For example, if we look at potassium and barium in terms of their Lewis structures, potassium only has 1 valence electron, whereas barium has 2, so losing 1 valence electron is much easier than losing 2 valence electrons, and that's why potassium is higher on the activity series than barium. Now, the problem is that potassium is actually higher up on the on the periodic table, meaning that barium actually has a larger atomic radius than potassium, and therefore, based on atomic radius, would be expected to lose electrons more easily. So the problem and the reason why the metal activity series is necessary is that a lot of the comparisons are more difficult to make, because when we compare multiple variables such as number of valence electrons, the atomic radius, etc., and especially when we get down here, when we get to looking at the mostly transition metals, this comparison is a lot harder to make. Therefore, what we can simplistically say is that the higher an element is on the metal activity series, i.e. the more reactive it is, the more easily that metal is to lose an electron as opposed to gain it, and the higher they are, the more easily that is able to be done. So in terms of using the metal activity series, we can take a look at a practice problem here where we have two single displacement reactions where we have barium as an element which may or may not displace calcium in an ionic compound in order to give us barium sulfate and calcium metal, and the opposite reaction where calcium can possibly displace barium in order to give us calcium sulfate and barium metal. Now, as we looked at in the previous video, one of these reactions is actually impossible to do because one of these metals is less reactive than the other. So even before we look at the metal activity series, we can make a prediction by looking at the periodic table. So if we look over at the alkaline earth metals, calcium is here and barium is here. Therefore, we can conclude that in terms of atomic radius, barium has a significantly greater atomic radius than, let me just write this carefully, than calcium. Therefore, its valence electrons are farther away from the nucleus, and the farther away these electrons are from its nucleus, the weaker the attraction is between the nuclear charge and the valence electrons. So if we write a more simplified visual comparison here, you can see that barium's valence shell is farther from the nucleus than calcium's, and therefore the attraction between the nucleus and barium's valence shell is weaker, which technically means that its ionization energy is going to be lower than calcium's, and therefore we would expect that barium is easier at losing electrons than calcium is. Now, what we can do after we've made our hypothesis is we can check the metal activity series and indeed see that barium is higher on the metal activity series than calcium is, and therefore it is easier for barium to lose electrons than calcium, thus confirming our hypothesis. So the conclusion is barium can indeed replace calcium because barium is the more reactive metal that is better at losing electrons, whereas if calcium is the less reactive metal, meaning that it is less likely to lose electrons, then there is no way that it can take barium's place here, and this second reaction is not possible, meaning the successful reaction would be reaction 1 here, which again we can predict using our periodic trends and confirm using the activity series that is provided to you here. Now, to test your knowledge of how to use this activity series, you can take a look at the practice problems below, which walked through relatively simple comparisons about which metal is most reactive in terms of how well it is able to lose electrons, going all the way to more application-based problems where you need to identify, based on the reactivity of both metals or both non-metals in the reaction, whether the reaction is possible or not.